And each of these colored curves are theoretical mass radius relations for fixed composition. So the solid blue, red, and magenta curves are for hypothetical 100% pure water ice, silicate, and iron bodies, respectively. And this is literally what this diagram looked like 6 years ago when I first started studying sub-Neptune-sized exoplanets. Back then, we really only had the masses and radii of the solar system planets. But of course, since then, planet hunters have been populating this diagram. So here are the planets known to date that were discovered by surveys other than Kepler, so Mirth, Corot, HAT, and radial velocity surveys. And here it just highlights the incredible contribution that Kepler, when combined with transient timing variations, kind of detailed dynamical analyses, and radial velocities, has made in populating this diagram. So each of these green points are Kepler planets that have been publicly announced to date, but we can look forward to many more Kepler planets with measured masses to be released in the near future. And I'll describe a little bit about those now. So the Kepler team has undertaken kind of a giant follow-up effort using Keck high-res to measure radial velocities to constrain the masses of Kepler planet candidates. And in this program, they've been focusing on planets that are smaller than 4 Earth radii, orbiting bright stars for which they might hope to get the radial velocity precision to constrain the planet mass. This has been a giant effort led by Jeff Marcy at UC Berkeley, and including kind of the entire Kepler team, extended Kepler team. And I've been very excited to be involved to help with the interpretation of these masses and radii. So as a result of this program, they've measured masses and radii for 52 Kepler planet candidates. So measuring masses for 42 Kepler transiting planets, and 10 more planets were discovered from radial velocity trends. Okay, and so these 42 new transiting Kepler planet candidates with mass constraints now more than double the number of sub-Neptune-sized planet candidates with mass constraints. So this is, and so here I'll just show all the current census of planets together with the color of each point scaled according to the amount of flux the planet's receiving from its host star. Now this is very exciting to me. There's so much information in this diagram, and it's very exciting to be moving beyond case studies of individual objects to study the statistical population as a whole. Now one trend that's readily visible in this diagram is kind of this paucity of planets, of high mass, high density planets here. And so now in the rest of my talk, I'll investigate this paucity of massive rocky planets in greater detail. Okay, so it turns out that one of the most robust insights that we can glean from an exoplanet's mass and radius is whether it needs volatiles. And by volatiles, I mean hydrogen, helium, or astrophysical ices. So I'd just like to highlight this curve, which is the mass-radius relation for a pure silicate body. This is effectively a rough upper limit on the radius of a rocky planet of a given mass. So planets larger than this are not rocky. They require volatiles, some hydrogen, helium, or water, or other ices. They can still have a rocky core. Rock can still make up a substantial fraction of these planet masses, but they require some sort of low-density volatile envelope to account for their large transit radii. While planets more dense than this limiting relation could potentially be comprised of iron and silicates alone. Okay, now one thing I like you to note is many of these planet points have rather large error bars on their masses especially, and on their radii. And so we need some way to robustly take these uncertainties into account when assessing which planets may be rocky. And so with that aim, I define this P rocky, this probability of being rocky parameter. So it's a measure of, given a planet's measured mass and radius, what's the probability that it's dense enough to be rocky? And so if we have a planet with some measured mass and radius and some uncertainties, here's kind of the observed mass radius distribution, then P rocky I've just defined as the fraction of this observed mass radius uncertainty regime that falls into this high density, potentially rocky region of mass radius space. So some planets that are well constrained to be in this high density, potentially rocky regime will have P rocky near 1, whereas low density planets will have P rocky near 0. Now I want to mention some of these mass constraints are marginal radial velocity detections or radial velocity upper limits. And in those cases, the radial velocity amplitude might leak into unphysical regimes corresponding to negative mass or even masses more dense than a pure iron ball. And so in those cases, after we apply the priors that the mass lie in what we consider a physically relevant regime, we can end up with non-Gaussian error ellipses. And so we take that into account. These mass RV kind of marginal and non-detections nonetheless still contain information about the planet mass and density. Okay, so evaluating P rocky for all transiting planets with mass constraints known to date, here's what we find. So this is planet radius and this probability of being rocky on the y-axis. So as you can see, smaller planets are more likely to be dense enough to be rocky. Planets larger than 2 Earth radii are typically not dense enough to be rocky, and then there's this transition regime between about 1.5 and 2 Earth radii. But now I'd like to take this a step further and ask, what do these current observations that we have tell us about the underlying distribution of planet properties? Now, before doing that, I should say something about selection effects. So Kepler's a transit survey, and as such, at a given planet mass, it's strongly biased towards finding lower density, larger planets. But then the Kepler objects that were selected for radial velocity follow-up, they were selected based on their radius and then followed up in a mass-blind way. So we might anticipate that at a given radius, we're not too strongly biased in how we're sampling, in how this sample is sampling the underlying distribution of planet masses. So with that assumption, I'll explore what this sample is telling us about how the fraction of planets dense enough to be rocky varies as a function of planet size. For this, I take a Bayesian approach. So I define some model for the fraction of planets dense enough to be rocky, assuming some simple functional form for how it depends on planet radius. And here I'm using A just to denote all the model parameters that will constrain based on the data. And then the likelihood of finding a given planet with a measured mass and radius based on our model, given our model, is then the probability that either, one, the planet is rocky based on its measured mass and radius, and we would select that a planet of that size is rocky given our model for the overall distribution of planets, or that the planet is not rocky given its measured mass and radius, and that we would kind of choose from the overall population a planet of that size that's not rocky. Thank you. And then we can apply Bayes' theorem combined with priors on the model parameters to measure the posterior probability of the of the model parameters conditioned on the data. Okay, so now let me give you an example, a simple example of how this works. So here, I'm taking kind of the simplest model that I could think of, essentially a step function, whereby all planets smaller than a given threshold radius are rocky, or dense enough to be rocky, and all planets larger than that threshold are too low density to be rocky. And now applying this Bayesian approach, we can measure the posterior probability distribution of this one parameter radius threshold. And here's what we find. So the pink shaded region kind of gives an estimate of the 1 sigma uncertainties on this posterior probability distribution estimated by bootstrapping. So the median in the simple step function model, the median threshold radius is 1.7 Earth radii, and the 95% confidence upper bound is 1.81 Earth radii. And these correspond, for a pure silicate body, these correspond to masses of about 5.7 and 6.9 Earth masses. Okay, but we can take a slightly more complicated model, because we might anticipate that there would be some range of radii over which planets could be either rocky or too low density to be rocky. So here's a kind of the next most simple model I came up with, kind of just taking a linear transition between rocky and non-rocky planets. And so now we have two model parameters, but we can take a similar approach to constrain them. Here's what we find. So here I'm plotting the minimum radius of planets that are too low density to be rocky on the x-axis, and the maximum radius of rocky planets on the y-axis. And these contours are the 1, 2, and 3 sigma confidence bounds. And so you can see with this model, we have with two parameters, we have a bit more freedom. Rocky planets can potentially exist, according to this model, to beyond 2 Earth radii. But if we look at what radius do no more than 5% of planets dense enough to be rocky, that's constrained within 2 sigma to be less than 1.85 Earth radii. Okay, and then we can compare these two models using Bayesian evidence to see which is preferred by the data. And it turns out that the simple step function is preferred. This Bayesian evidence criteria includes kind of an Occam's razor that penalizes models if they that are more complex with more parameters. So essentially what this is telling us is that a step function model actually fits the data pretty well, and that if we want to resolve the structure in kind of the distribution of planets that are dense enough to be rocky and not dense enough to be rocky, we'll need more mass radius measurements with smaller uncertainties before we can do that. Okay, so now I'd just like to conclude and give you the main takeaway points that I hope you remember from my talk. And one is to stay tuned for new mass constraints on 42 transiting Kepler planet candidates. And that, second, planets larger than 1.8 Earth radii are likely not rocky. Thank you.
Thank you, Leslie. Any questions? Yes.
I remember Jonathan Fortney mentioning in his talk with the Kepler 36 system how you could account for the different densities based on their different masses. So I was curious, is there a physical motivation for making the cutoff for your model in radius space instead of mass space, or is it just because you know the radius so much better?
So the motivation for exploring the fraction of planets that are dense enough to be rocky as a function of planet radius is because of the selection biases that I mentioned. So, yeah, I anticipate, just based on the way the majority of these planets were selected, that at a given radius, the distribution of masses is not strongly biased. But I think at a given mass, the distribution of radii is. So that's why I'm exploring it in this way. I agree, kind of, for comparing to formation models, probably as a function of mass would give a more direct comparison.
Thanks.
Yes, over there.
Hi, Sloan Viktorovich, UC Santa Cruz. That was a very nice talk. So I have a question, though, about the smaller planets tend to be denser, because when you get below 1 Earth radius, it looks like your probability for Rocky is approaching 50%. Is that just a radial velocity upper limit?
Yeah, those are cases where, yes, you just have a radial velocity upper limit, and our information about those planets are essentially, were prior dominated in those small planets. So yeah, a lot of, so yes, that's an excellent point.
And the last question there, please.
Hi, Leslie. You can imagine that planets just below the pure rock curve. I was wondering how you handled those in terms of those potentially could have a higher iron to rock ratio, and then maybe you could add a little water so that you wouldn't necessarily be at 100%. I was just wondering how you graded from along that boundary there.
Yeah, so here in this analysis, I've essentially been just considering kind of binary, is the planet dense enough to be rocky based on that pure silicate mass radius relation or not. I have repeated the analysis, instead taking an Earth-like composition threshold, and for that, the limiting radii decrease, but the masses that they correspond to increase a little bit. So yeah, the criterion that planets larger than 1.8 Earth radii are non-rocky still holds, but the mass that corresponds to increases to about 9 Earth masses or so.
Okay, let's thank Leslie once again.